My name is Danny, and we will talk about ground vibration testing today. And next week we are going to have like a live demo of the actual test. Okay. Today we'll cover basic theory and procedures that you all need to to understand before you dive in uh, vibration testing. Okay, before you can do model testing. Okay. Personally, I am doing this for 10 plus years in the aerospace industry, and this is one of the more important, more interesting tests that you can do in the development process. Okay, my goals from this are these three. I want you to understand why this is important, what is required, and what is the general procedure to do such a test. I want you to be clear what can and cannot be achieved in this test. And I also have one more, and I want to try to get you motivated enough so you can start playing with the equipment that we have here at Duke. We have all the necessary tools, but it's not used as much as I would like it to be. Okay, so it's kind of up to you, and my goal is here is to get you interested enough in this. This is the basic outline. Before we dive in, I wanted to be kind of interactive presentation. So anytime you have a question, please ask. The same goes to you, KTH. And yeah, so and one more thing, my experience is with aerospace, so my examples are planes and stuff that fly. Okay, but it applies to anything. This is the general outline. We are going to talk about what is GVT, why is this important, difference between analysis and test, general vibration test types, go over the requirements, the test procedures, and all bits and pieces that make a whole test setup and test. Before we dive in, I understand that we are doing this presentation in the middle of the semester, and as far as I know, you are after the midterm, right? Okay, so we have several basic questions just to understand that we are on the same page, just for the presentation to be relevant. Okay, and yeah, feel free to jump in and answer this. So well, first of all, what are natural frequencies? Come on, you had a midterm here. KTH, anyone? Okay. Okay.
Hello?
Yes.
The natural frequency is the frequency to which system tends to oscillate by itself.
That's that's right. So natural frequency is just your structure, your system. If you kind of hit it and don't force anything on it, then the frequencies that it will vibrate will be in the natural frequencies. What are the natural modes? Okay. Natural modes are the vibration shape that are associated with any natural frequency. So it comes in pairs. Natural frequency comes with natural mode. Okay, I'll have some figure later in the PowerPoint. What about damping? How can you determine damping in your structure? Yeah. Yeah, but I'm talking more of you have your plane here. What are you? How are you determining the damping? So the answer is damping is probably the most elusive quantity. So it can be determined only by test, or kind of inferred from previous experience. But the real damping of your current structure can be determined by test only. What about frequency response function, FRFs? KTH? Okay. So frequency response function is basically the dynamic property of your structure. And if we go a little further, what determines the dynamic response of your structure, as we all live in linear course, so we take the input multiplied by property of the structure, which is called the FRF, we end up with the output, the dynamic response of the structure. This sounds familiar? Okay, it's 1 over omega square plus 2 xi omega. Sounds familiar? Okay. And the most important question of all is who cares? Why are this important? Okay. Anyone? Okay. So to emphasize all this, we'll look at beams. Everyone knows what vibrating beam is. So the F's will be the natural frequencies, and you see the shape. This is called the first bending, second bending, third bending. The same goes for free beam. So the natural frequency will be the frequency where our beam will oscillate on with no external forcing. Okay, and the mode will be the shape, the vibrating shape. It's unique and it comes with its own frequency. So for the remainder of this presentation and throughout your careers, I want you to understand that knowing these properties, the dynamic properties of the structure, is very good idea, because it kind of controls all of your responses, all of your dynamic stresses, and all the dynamic encounters that your structure will get throughout its life and throughout the design process. So if we're talking about force response or dynamic loads or dynamic stresses, will be all influenced by the dynamic properties of your structure. So anything that you can mount inside or design thicknesses or stiffnesses will be controlled by this. If you are talking about aeroelasticity, where our elastic properties will be combined with aerodynamic loads, this is very important, and it's even enhanced when you add the control loop inside. So you are starting to control elastic structure under aerodynamic loads. This tends to be very complicated, and you simply have to know the properties, the elastic properties, the dynamic properties of your structure. Okay, so everything here is affected by those properties. Just to show you some real-world examples, we're talking about fighter jets, or jet engines, or just missiles. If you're designing this, you're collaborating with the design of those structures. You need to know the dynamic properties of these structures. Okay, it's as simple as this. The proper design will involve knowing and using these properties. Okay, questions so far? Sweden? No. Okay. Okay, this were the preliminaries. Now let's dive into the essence of the presentation. So what is GVT? It is simply experimental way to extract dynamic properties of your structure. And dynamic properties, we also call them modal properties, because we are playing in the modal domain. GVT stands for ground vibration test, and EMA is the more recent acronym for the same thing. It's experimental model analysis. When we are talking about dynamic properties, these are simply the frequencies, natural frequencies, modes, and modal stiffness, mass, and damping. And as I mentioned before, damping is probably the only one that you can determine with test only. All of the others you can model at some to some degree, but damping is can be determined through the test. So first, I know that you're experienced people, right? So the first question might be, what about finite elements? Finite elements are used extensively in the industry. You probably use them by yourself, and it's used to model pretty much everything. It's very accurate, and it's very capable. The whole approach, and it tends to be very reliable if you know what you're doing. So what's the problem? The question is, why won't we just model the structure and ditch the test altogether? So this is an open question to Sweden also. What do you think? What's the challenge here? Okay. No one. Yeah.
You're talking about, like, is it very hard to do the meshing for the structures?
Well, it's not that hard. It came a long way. Okay.
I mean, you only need to validate your theoretical result.
That's right. That's the main reason. So your model, no matter how good you're building it, you still have to validate your model. Okay. So your equations are only as good as if you know that they are correct, right? So we are using test for this. Okay, and also finite elements can help you with the reverse problem. Reverse problem being this is your plane, your track. What are the natural frequencies? Okay, so you cannot do anything with finite elements. You need to run a test. Okay. So far, questions? Sweden? Okay, nothing. Okay, we talked about the ground vibration test. We talked about finite elements. Let's go and distinguish between the two approaches. What do we do in each one in order to get our model properties? So for modeling, we usually do with the CAD data. It's modeled in some way, drawings and all kinds of stuff. For example, stiffnesses of the pistons, all kinds of friction coefficients. Then we build our model, and meshing is not that hard, as you said. So it becomes easy every year. Then inside the code, the program will build your model matrices, the mass, stiffness, and damping matrices, and only then, if you run the model analysis, you will get natural frequencies and natural modes. Okay, so this goes with finite elements. For test, we do a different way. First of all, you need to have a structure. There's no test without structure. So we excite the structure with forces. We record the responses from the structure. Then we calculate the natural frequencies and modes, and only then we can compute the model properties. Okay. Questions so far? Okay. Let's continue. Before we dive into the actual model testing and ground vibration testing, I want to mention briefly one other vibration test that exists in the industry, and we call it the environmental test. So environmental tests are exactly as it sounds like. So you take your structure and you subject it to dynamic loads of the environment, whether it be a bumpy road or turbulence. So you put it on a slip table. So it's see, This is the table. This is your structure. The table simply allows the shaker, this huge structure here, to vibrate it with force. And this test, it's important, but it requires very big shakers, which tend to be limited by the mass of your structure in test. You need special facilities for this. It is extremely violent and noisy test, and it can potentially kill your structure. So if you are going to environmental test, be ready that your hardware may not return in one piece. It's very violent. So to summarize this, it's like raging Godzilla. Okay? As opposed to this, GVT, the model test, is extremely elegant. We are using very small shakers. I have an example here. We'll talk about it later. We can do this anywhere. We can come to a structure. Instead of it coming to us, we can attach our sensors and shakers, do the test, and return the structure in one piece. This is powerful. This is not a non-destructive test. So I can fully characterize my structure, my plane, and leave it to continue its purpose. Extremely elegant. It's like 007 as opposed to Godzilla. Okay. Questions so far? Go ahead. Okay. Okay, we talked about generally what the test is. What is required to run a test? We need three things. First of all, we need a structure. Of course, it must make sense for the project. This is more important during the design process, where the structure tend to have full, for example, only the frame without the internal hardware. So maybe missing some components. You need to be aware of this before you do the test. And you, of course, need to satisfy the right boundary conditions. This is more important for the free. For example, planes are during the test are on the ground, but we don't care about this. We need the natural frequencies and modes in the air. So how do you do this? And second thing is you need to know what the test is for. So there is no test before you know what you are going to extract from it. And the third thing is you need to have nice equipment, capable hardware and software. Let's go over each one of these to mention in detail. So first of all, structure. What's in the test? So if you think about this, this is not so stupid question. So I gathered some pictures here. For example, look at this bridge. So what's in the test? It's obviously it's the bridge, but it also contains the trucks on top of it. So it's loaded structure. Okay? And in this case, obviously the boundary conditions are satisfied because it's a bridge that stands somewhere. Okay, what about this jet plane? Being fighter jet, you need to be aware what's under the wings. So what configuration are we testing? What's the status of the fuel? Have full, quarter full, full tanks? What's generally what's inside, what's not? So you're gathering model data of the structure. You need to connect it to the configuration of the structure. Okay. What about this? So this is kind of some kind of frame which is suspended from these fixtures. So the structure in test is the frame which is suspended from the fixtures. It can be or not, can be relevant or not for the correct boundary conditions. So be aware of this. Be aware of what's in your test. Regarding the free boundary conditions. So we're talking about planes. As I mentioned, we don't care about plane on the ground. We care about plane flying in the air. So how do we implement free boundary conditions? There are three ways to do this, and we're going to go from the cheapest to the most expensive. Okay. First of all, you deflate the tires. So what you do, what it achieves, is essentially you're having soft pillow for your plane to stand on, and the frequency of the plane on the deflated tires will be low enough to not interfere with the elastic modes and frequencies. Okay, this is obviously the simplest way to do. The next thing are bungees. Bungees are simply flexible cords that you can suspend your plane from frames. This is the picture here, and it's very neat. So when it's suspended, you can come to it and just heave it with no much effort, and it does exactly what the tires achieve. This mode, the mode of the plane on the bungees, will be low enough so that elastic properties won't be affected. And the most expensive and elaborate means will be the pneumatic or hydraulic suspension. This is this picture. This is basically additional equipment that will raise your plane above the ground on a nice soft cushion. And it's not just the equipment. It also needs its own control system to control the air pressure and not interfere with the excitation forces. So basically, this is usually only available to the big companies like Boeing, Airbus. It's not available to anyone. Okay, but bungees are very common and pretty much used everywhere. Questions so far? KTH? Okay. Let's talk about the equipment. We need several things. First of all, we need the data acquisition hardware, which has to be capable of an analog input and output. Output will be for controlling the shakers. Analog inputs will take the signals in. We'll have to simultaneously sample all of the channels. It has to be with nice sampling resolution and high acquisition rate. The software needs to work with the hardware, and it acquires the data, controls the shakers, and also manages the whole test, the whole generated data from the test. And there is a lot of data coming from this test. We need something to excite the structure with shakers or hammers. We need to record the responses with accelerometers, and we need force sensors to record the input forces, and of course we need cables to connect all of it. Okay. General procedure of the test. It's not so hard. So first we get a structure. We attach accelerometers. We decide how we're going to excite the structure. We're recording the excitation and the responses. We calculate FRFs, and we extract model parameters. So the bullets 5 and 6 are done inside the software. So you just appreciate the modern tools that you have now. Okay, for this. It used to be calculated by hand. Now, the example goes here. So we have this plane here. Our excitation comes from the shaker on the wing. We also connect several accelerometers on the wing. We excite the structure. We record the responses. We divide one by the other, and we get the frequency response function. From this, we can extract all of the rest. Okay, so these are the mechanics, and the part that I always add is this. So tests in general, and this in particular, tend to generate a lot of junk during the procedure, and it's perfectly fine. But what's not fine is to use this junk further on. Okay, so you need to be aware of if you are getting something physical or just something that does not make sense. Okay, so we are still not eliminating this. So this sounds very simple, right? So actually, it's much more complicated inside. So the tools are used to estimate the FRFs are statistical tools, very complicated mathematics. It's some tools to eliminate noise, to filter all the signals. So what goes in the background is really not that important for the front user. Just be aware of what's going on there, and I just find the other way much simpler to understand. Just divide by one by the other. Okay, so let's go the preliminaries. Now we dive into the actual hardware. Questions so far? Sweden? I see a hand there, or just no? Okay. Okay, so everything is clear. Okay, let's talk about the excitation means. First of all, we have the model hammer. So they come in different sizes and shapes. Heavier hammers tend to excite bigger structures. So what's so special about it is that we have a force sensor inside the head. So once we hit the structure, the excitation is recorded. Okay, I have an example here of a tiny one. So it's yeah, this is the hammer, the force sensor being here. So if you want to check it out afterwards, you can. So hammers are nice because they are suitable for field work. If you want to come to a bridge, for example, you are not going to set up anything more elaborate. The setup time is short, but you kind of pay for it for long test times. You need to go over the structure and hit it in different points. It can be used for simple structures or to get first estimates to place your shakers. Okay, for shakers, they are more complicated. First of all, they can deliver various types of excitation. So if hammer can do only impact input, shakers can do sine, random, chirp signals. You can even play your favorite tune through the shaker, through the structure. It's suitable for complex structures because you can drive more than one simultaneously. If you have something complicated 3D shape, you can excite it from different directions and with different force levels. The setup time is longer because you, besides attaching the shaker to the structure, you also need to suspend the shaker from somewhere. So this is a model shaker. All of the KTH, it's this one. All of the shaker, they have this funny rod on top of it, and the force sensor goes here. So any idea why we need this flexible thing? Okay. So this rod is called sting, and its only purpose is to deliver the force in one direction. It uncouples the excitation from all the sides, because we want the properties of the structure, not the structure with the shaker. Okay. Now for the sensors, we have usually we use accelerometers to record the responses, and force sensors to record the inputs from the shakers or from the hammer. These are usually piezoelectric type. Okay, so these two here are accelerometers. You see, these are cubes with area to attach the cable, and these two are force sensors. So you see the thread from both sides. From one side it goes to the shaker, and the other side will go to the structure. The procedure, the model procedure, requires that each time you have excitation point, you also have accelerometer there. So this is called the drive point measurements. You excite the structure from one point, and you have to have the response measurement there. So for these purposes, companies invented this thing. So it's a combined unit of force sensors and accelerometer, with two outputs. This is called impedance head. Just to be aware of it. It's more convenient to use instead of two sensors. Just use one. Okay, finished with the hardware KTH. Any questions so far? Okay. Okay, now let's talk about what we do during the test, and specifically how do we identify all the model shapes during the test. So this is, we call this the modal model. Okay, so we go from this beautiful structure, beautiful plane, into kind of ugly doodling. Okay, and the reason for this is that this scribble, this sketch, will help me to determine the mode shapes. Imagine that you have a test with 20, 100, maybe a couple of thousand sensors, and to make sense of all of them, it's really hard. But with this simple sketch, simple model, it can be much easier. So you see, from this I can go for the first bending of this of the wings, or the second, or the antisymmetric torsion from the same plane. Okay, the important thing to know that this model has no physical meaning. It's just it exists only for visualization purposes. That's it. It's nice to have, but it has no further meaning besides the test. Okay. Okay, so the question is, how many accelerometers, shakers, or or tapping points you are going to use during the test? Knowing that the answer to this question will directly influence your resolution of your test. Okay. And to answer this, you need to think about three things. First of all, what's the purpose of your test? What do you have as your equipment? And how much time do you have? Okay, so the purpose of the test can be, for example, simply measuring natural frequencies. For these purposes, I can use even only one accelerometer if I don't care about the mode shapes. Okay, if on the other hand I need to map all the modes, I will instrument my structure with much more accelerometers. Okay, what equipment do you have? So this equipment is expensive, and company won't buy equipment just because you need extra channels. Okay, so what you have in house, that's what you're going to use. If you have a box with 8 channels, like we have here at Duke, so with all your desire, you can have 30 channels sampling simultaneously. Just don't have it. And of course, how much time you have. So it's the time is not only the setup time, also the disassembly time. You will see it next week, but this test setup tends to be complicated very quickly. Now let's talk briefly about the resolution, and I have my pen here. Look at this beam. And this beam is equipped with a lot of accelerometers, and you see that the first bending, second bending, and the third bending are identified pretty nicely. You see all the curves. Now imagine for a second that you, instead of the 13 pieces that you have along the beam, you only have 3. So you have one on each sides and one in the middle. So how would the first bending will look like? Okay, so instead of this, it will be something like this with straight line, right? Oops. So you have reading only here and on 2 sides. What about the second bending? You see all these nice curves, but if you have only 3 accelerometers, you will have a straight line. Okay, the reading is here, here, and here. Okay, so if you don't know what you're expecting to have, you can have really hard time to identifying the mode shapes. What about this, the third mode? So instead of this nice nice snaky-like feature, you will have only the straight line. Okay, so that's be aware that with fewer accelerometers, you won't have as nice modes as you can have with more of them. Okay, let's. Okay. Okay, now linearity and nonlinear structure. So one thing that it's important to mention that the whole theory of ground vibration testing is based on the assumption that your structure is linear. All the underlying mathematics and everything that you can extract based on this. And you know that there are no linear structures, right? No real linear structures. So, but most of the structures, the good news, the most of the structures are linear enough for this test to make sense, and for the results to be useful. That said, if you are looking for local nonlinearities and local some dependence on force on excitation levels or something else, you can investigate these nonlinearities with the standard equipment. KTH, any questions so far? Okay. We're almost done. I want to summarize this presentation with several things to remember. First of all, before you do the test, know the purpose of the test. Don't start without knowing this. Be aware of what you are measuring and in what direction. This tends to be very important when you have more complicated structures than standard beam. Sampling rate versus desired frequency. You need at least twice of a sampling rate than your highest frequency in the system. If you can go higher, do so. Always use averaging. We will see this next week, but there is no test that will get you any useful results with one excitation and one result. You always average your responses. Sensors add mass. Okay, be aware of this. So the structure in the test is the structure with your sensors attached. It can be measurable or it can be not. So be aware of this. And of course, your models are not always right. This is important. My point here is just that if you are okay with your test, with your procedure, and with your results, and you are not getting the same results or the same frequencies in your finite element model or somewhere else, your model is wrong. Okay, so don't waste any time with searching stuff that isn't there. Okay, thank you. Any questions? I can answer them. Sweden? Just let me know that you are alive or there are no questions.
Hi, I do have a question.
Sure, yeah.
So when you apply the excitation through a hammer, you need to know how much excitation you're putting.
Okay, can I ask you to talk to the mic again? I didn't hear the whole question.
So if you excite through a hammer, do you need to know how much force you're exciting with it?
Okay, so the question was if you need to know the force that you are exciting. The answer is no, because you have the force sensor that will measure this for you.
Yeah. Good, thank you.
Okay, here? No, nothing? Okay. I will finish with just a final slide with what we have at Duke here. We have a nice data acquisition box with eight sampling channels, and that can drive 2 shakers at the same time. It's 24-bit, 200 kilohertz of simultaneous sampling. It is bundled with state-of-the-art software that will do all the excitation for you, will record all the responses, and will manage the data. And also we have shakers, hammers, accelerometers, and all kinds of stuff to get you through a test.